Good morning, this is Dr. Turner for Integrated Math 3. Today we're covering 6.5. We're going to be wrapping up our review unit on exponential functions. 6.5 is titled Growth and Decay, and unfortunately it does involve word problems. It's just the nature of this last bit of the exponential review. Again, it is review, and we've covered this exact topic in Integrated Math 1, so hopefully it's not too bad, but there are word problems, so just keep that in mind. So we'll go ahead and get started. With exponential functions, we're starting out with the parent function, which is, of course, y equals a times b to the x. Now, this works okay for us when we're looking at problems where we are multiplying or dividing by a set value that's an integer or whole number. So if I'm doubling or tripling something, I can typically use just this base parent function. If you recall, we talked about this in 6.1, but when we looked at linear functions way back when, y equals mx plus b is slope-intercept form, and each of those variables has a purpose. But when we're talking about word problems, our m represented our rate of change, and b represented our initial value. In exponential functions, our a and b values are going to serve that same purpose. Our a is going to indicate our initial value, and then the b does indicate what we might think of as being a rate of change, but just like we did with 6.1, the difference between arithmetic and geometric sequences, we're not adding the same amount each time here. We're either multiplying or dividing. So you can kind of think of b as a rate of change, if you will, but more commonly we'll refer to that as a ratio or multiplicative, depending on the textbook. Excuse me. Depending on the textbook. You'll have depending on the textbook, you'll have different vocabulary terms for that. Now, as I mentioned, that only really works if my rate of change is doubling, tripling. It's a whole value. More commonly, when we're looking at word problems involving growth or decay, we're going to change this a little bit. And the most common application of growth and decay is compound interest. So that is given by the formula a equals p times 1 plus r to the t. So sort of similar, a is going to be our output. So a is taking the place of y. P represents the principal amount, or initial amount. That's the same thing as my initial value. R is going to represent a rate as a percent. And then T is the same as X. That's our input. But because with compound interest, we're talking about amount of money that's being earned or lost over time, we're doing T for time. This is in terms of compound interest or growth or decay models where we're looking at the change annually, meaning it changes every year. If you were to change this, and let's say it was monthly or daily, then the formula changes a little bit. If we were in person, we'd look at more of those types of examples, but because we're doing this all online, we're going to keep it simple, and we're going to stick with the base compound interest formula. Okay. So let's start off with a simple example. Let's say I have a population of rabbits. I have 10 rabbits, and that population triples over 6 years. I want to know how many rabbits there are after 6 years. So because I have a simple rate of change, quote unquote, or a simple ratio, I can use the top formula, a times b to the x. So I start out with 10. That's going to be a. My rate of change is tripling, so 3. And then I want to know how many there are after 6 years. So it would be 3 to the 6th. A lot of these, particularly when we get into percents, are going to involve calculator work. However, you still need to be able to come up with the formula. On the CAS test, it's very common for them to ask you for, what question part A might just be the formula, where question B is the response. So be sure to keep that in mind. I do want to see your formulas as you're doing your work for me for the 6.5 assignment. And then once you do that, then you just type it in the calculator. 10 times 3 to the 6th, you get 7,290. Okay. Now, because this is a word problem, my expectation is that you are answering in a complete sentence. Anytime you're given a word problem, you should be answering in sentences. It doesn't have to be long and drawn out, but it does need to be a complete sentences. So, something like, after 6 years, there will be 7,290 rabbits. Again, not a long sentence, but a complete one. And we'll change that font size so it's actually legible. Take it up another notch there. Okay. So after 6 years, there will be 7,290 rabbits. Okay. So I expect to see the equation, and then I also expect to see that complete sentence for full credit. Okay. Those examples are less common. If you're going along with the supplemental resources or the textbook, you have a few of those thrown in there. Majority are dealing with percentage changes. So you might have a problem like an investment account earns 3.5, well, maybe keep it simple, 3% interest annually. How much is in the account after, say, 12 years if the initial investment is $100,000? Again, change that so that we can actually read it. It's not so tiny. So an investment account earns 3% interest annually. How much is in the account after 12 years if the initial investment is $100,000? Okay. So anytime we have a percentage, we're going to need to use that second formula. A equals P times 1 plus R to the T. So we go in and plug in chug here. P is the principal, the initial amount. So we're investing $100,000. So that's going to go in for P times 1, and we're going to leave that there for a second. And remember, T is time in years, so I'm going to have a 12 here. Now up top, R is the rate. However, remember that you cannot just plug in a percentage into an equation. You have to change it to be a decimal. That's a middle school math concept, but if it's been a while, what you do, if I want to change 3% to a decimal, okay, you take the decimal place, which would be at the end, and you move it over 2 spaces. If there are any gaps, which there are here, then you fill in a 0. So 3% is 0.03. So 0.03 is what I would put in for R. So you should have 100,000 times 1 plus 0.03, and that's raised to the 12th power. Most common mistake in this section is right here for the rate. Some students will just put a 3 there. Some students will put a 0.3 there. It has to be 0.03 or the numbers are going to be way off. So be careful with that. Once I have my equation written, I can't talk today, then it's just calculator work. So 100,000 times 1 plus 0.03. And I'm going to raise that to the 12th power. So I have 142,576. 0.088685. Second most common mistake is that I'll have a lot of students that'll give me this as an answer. The problem with this is that we're talking about money. So if I'm talking about money, I don't need all those decimal places. I need to round it to the nearest cent, which would be the hundredths place or 2 places after the decimal. So yes, that is technically correct from a calculator perspective, but in the context of this problem, I need to write it as money. So it would be $142,000, $142,576, and then round it, it would be 9 cents. So that would be a correct answer. And then, of course, because this is a word problem, I would need to write out a complete sentence. So the account after 12 years will have a balance of, and then the amount, $142,000, $576.09. Not a long sentence, just a complete one. Both of these are examples of exponential growth. The same formula can be used for exponential decay. Some books will write it separately. Some books will write it as a single equation, so they'll put a plus or minus symbol there to indicate that it can be growth or decay. Now, just as we saw in example 2 here, most of these problems are not going to say add or subtract. You have to look for the vocabulary terms that indicate is this a growth problem or a decay problem. So anytime it says interest earned, profit, population growth, expansion, any of those types of terms are indicating growth, whereas if I was looking for a decay problem where it's declining, I would be looking for decline, depreciates, loss in value. Anything like that is going to indicate where I'm subtracting instead of adding. So let's say do number 3 here, and let's say a baseball card worth $1,000 in 1999 depreciates by a rate of 5% annually. What is the card worth today? So let's make that bigger first. This one's a little bit, not tricky, but we got to be careful with what specifically we're being asked to do. Okay, so first off, it does say depreciate. That means I'm going to have subtraction instead of addition. Okay, so it's going to be subtraction, and I can start setting this up. So I have an initial value of $1,000. From 1, it's depreciating by 5%. So if you need to do the scratch work, remember, move that decimal over twice. That's 0.05. And then I need to raise it to some power. Now remember that t is always the number of years. So a common mistake here is students will just plug in 1999 because that's the time that's given. But I don't want 1,999 years there. I want to know what it's worth today. So what you would do is take the year today, 2021, subtract the original year, 1999. So between 1999 and now, assuming the year 2021, that would be 22 years that the card is depreciated. So that's the value that goes in for t. Again, very common mistake. Students get confused if it doesn't say specifically how many years. So that's something to look for. Now that I have the problem set up, I can use my calculator, 1,000 times 1 minus 0.05, and I'm raising that to the 22nd power. Remember, this is money. So I have $323.53. So the card today is worth $323.53. Again, what I'm looking for this assignment, I want to see your equation. I don't need to see your calculator work, and then I want a complete sentence. That's it for today, guys. If you have any questions, please reach out to me. Otherwise, have a good day, and I will talk to you soon. Bye.